All right, folks, coming at you from my house right next to your fire. All right, what I have set up is something to help you visualize torque, and that's what we're going to do is calculate torques and distances here. Thank you, Jimi Hendrix. All right. What I want you to then think about is if this is obviously a meter stick that I have a weight hanging from, and it is then anchored to the wall here, and it is pivoting about a point that is right there. So this is the pivot point, and it's got a center mass right there at the 50, and the weight is at the other end here. So what we're going to do is learn how to sum all of the forces on this beam, and we're going to then learn how to sum the torques on the beam. All right? Now, the summing of the forces is usually pretty easy. It's just summing up all the x's and y's. So right now, what I have on this base down there, you can see that X arrow pointing outward from the wall. That's because the wall itself is pushing outward, so there's a force in the X. You see this arrow right there pointing upward. That's because the floor is pointing upward, so that's a Y row. That's a Y row due to the center mass, the weight of the beam. This is a Y row due to the weight that I have hanging there. This string now is the only thing that's not tugging in an X or a Y. Okay, so what you would do with that is turn it into an X and Y, which is pretty easy. You would either go over and up, or you would go up and over, which then it just depends on what numbers are given in the problem. They'll usually give you this angle here. They may give you this angle here, which you could then use to go around. The horn is what I call it, to get those three angles for a triangle and have to add up to 180. That will let you figure out what that particular angle is right there. Maybe they'll give you some numbers up here if it's anchored to a ceiling up there, whatever. Maybe it's anchored up to a ceiling there. It just depends, sorry, but usually the strategy you use is to go around the horn to get what the angles are, all right, to sum them in an X and a Y. There will always be two things you don't know for that X and Y, because down here is usually what you'll end up calculating. You're not going to know the force that the wall is exerting, and you're not going to know the force that the floor is exerting. You'll probably know this, you'll probably know that. You will not know the X and Y components of this. You may not know the tension, okay? So it depends on what's known and what's unknown as to what strategery you'll end up having to use, okay? So the next thing I want you to visualize is torque, all right? I mentioned a pivot point, which is down here where these two arrows are. See, there's two arrows acting on the pivot point, a Y and an X. So if I put a little triangle right there and I say, okay, I'm going to sum the torques at that location, this one right down there, then I've immediately eliminated those two arrows. I don't need to know what they are because those two arrows are 0 meters away from the pivot point, that triangle. So the torque that's being exerted by those two immediately go away. So then what I'll do is I'll come up here and I see the torque due to gravity is making this item want to rotate that way, which is counterclockwise. That's going to be a positive torque. This item then is a string pulling that way. It makes it want to rotate counterclockwise, so that is a positive torque. This is a gravitational torque, making it want to rotate clockwise. That again is negative, all right? So clockwise is negative, counterclockwise is positive. I think that's what I said earlier. I'm sorry if I misspoke it. There's two things you need to know for torque, a force and a distance, and those two have to be perpendicular to each other, okay? The distances I made pretty easy, all right? And I'm going to move you up a little closer. If you can tell, I don't know, but that's at the 50. I did that on purpose. This is at the 75. That's 3/4 of the L. I did that on purpose, okay? So this is L over 2. That's just 3/4 L. That's on the very end, obviously. That's going to be the full L. All right, so what I'm going to do now is show you how to get torques that are forces and radiuses, provided those F's and R's are perpendicular to each other. In this case, they are going to be perpendicular to this meter stick here, the beam. The one that's down here is there just for measurement purposes. All right, that meter stick down there is there just to help you measure stuff. Okay, but I put this together to help us visualize parallel and perpendicular to the beam. All right, to this meter stick. Okay. The one that I will spend a little bit of time talking about is this string right here. This is the one you'll usually break into a parallel and perpendicular to the beam, all right? Because the beam's radius is this. So if I were to draw the direction that the radius is pointing, it's that way. The torque is being applied that way. That's not a 90-degree angle, okay? Remember, when we calculate torque, it has to be at a 90-degree angle. So what I'm going to do is take the force that's inside that string, the tension, and I'm going to break it into a perpendicular and a parallel component. All right, it's going to be perpendicular to the beam, and it's going to be parallel to the beam, and it's going to end up right there. See how that green is perpendicular to the 2x4? That's what I'm going to do. Make it perpendicular to, not the 2x4, sorry, the meter sticks. Oftentimes when I do this, I use 2x4s. Okay, so that's what I'm going to do. This arrow is one that I already kind of have put together for it. Can you tell this arrow is at right angles to the meter stick? Hopefully it's ish. All right, it may not be perfect, but hopefully it's ish. Okay, now what I want you to realize is I have this leg is perpendicular to the beam, that arrow is parallel to the beam, and that string is now cutting across that arrow, this meter stick, that string is going across it. So I have alternate interior angles, don't I? Like I said, they probably give you this angle in the question. They probably give that one to you. You can figure out what that one is, which means you can figure out what this angle is, right? Because this angle, that one right there, is the one whose sine is the torque component, right? And we said when you multiply forces and radiuses to get torque, it's got to be the sine of the angle between them. And that's this angle right here. The sine of that component is the torque angle. All right? That angle right there. Now, how do you get that angle? You know it's the same as this angle because this parallel and that beam are, again, they're parallel to one another. So if you know that angle, you also know that angle. So you can take a radius times the force and multiply by the sine of the angle between them because that sine is the same as that one. Another thing you can visualize, hopefully, is if I draw the 2x4, which is, or not the 2x4, sorry, the meter stick, which is going that way. That's the direction that the stick is. The string is that way, isn't it? If you put vectors tail to tail, that's when you multiply vectors, put them tail to tail. So I'm going to take this string right here, and I'm going to put the tail of it at the end of the radius vector, all right? So that radius vector I know is 3/4 of a meter stick. That's the length of that vector. The string is pulling that way with some tension. I have no idea. But remember, that's tail to tip, right? If I put them tail to multiply vectors, I'll put it right there. That's the tension, where this radius and that tension, that force, are tail to tail. This is the angle between them, right? So I have a force times a radius, and I'm going to multiply that by the sine of theta. Now, do you remember? The sine of this angle is going to be exactly the same, which that angle is what I drew right there. This is theta. that angle. Do you remember? Supplements have the same sign, don't they? So that means this angle is also the same one. So if you know that angle, you are multiplying by the sine of the angle between them. It gives you the same resultant. So the force times the radius times the sine of the angle between them will get you the torque applied by that perpendicular component. Okay, now what I'm not going to do is break the gravity vector into parallel and perpendicular. I could, or this one into perpendicular and parallel. I could. I mean, it would just be as simple as doing something like that, right? But what I want to, well, should go over this real quick, whatever, fine. That angle is the one that has opposite it the torque component. But hopefully you can tell, gosh, this arrow is parallel to the beam, isn't it? So if I know that angle, I also know that angle. Take the sine, that's the perpendicular component. Something else I want you to realize, though, is if you don't want to break that into pieces, what if you just go straight down on the center mass or the weight vector? If you just go straight down, you're going to hit this other meter stick that, again, I have put there for reference purposes, just for measuring. But can you tell, again, if I go straight down from this center mass, I'm going to hit a radius that's perpendicular to where that force is located. So this force is going down here. So now I can multiply a force times a perpendicular radius. Now I'm not going to go along the beam to get to that distance. It's L over 2. But this distance here is the one that is perpendicular to the force, because the force is in a y. That means perpendicular to the y is in an x. So if I want to get that distance where this arrow bangs into this side of a triangle here, it's going to be adjacent to this angle, right? That's a cosine if they give it to you here. But if you know this angle, that's the sine also, right? That's the sine of this. So I want you to associate sines with torques, forces, and radiuses. Sometimes, though, to get that distance, it's just as easy to just call this the cosine of that. But you all know that cosine of this angle is the same as the sine of that angle, isn't it? So if you know this angle, you can push the sine button to get that distance, okay? You could also break it down into the sides that I showed you for that weight hanging up there. Or again, you could do the same thing for this weight hanging up here. Again, just go straight down and you can get the distance wherever it hits that stick by taking the cosine of this, which again, the cosine of that would be the same as the sine of this, which you know the sine of just this piece is equal to the sine of that piece of that angle, which is the torque side. So whether you're pushing cosine or sine, as long as it's referencing the appropriate side that gets you perpendicular, it's going to work, okay? But please remember, associate torques with forces times radiuses times cosines of angles, all right? And remember these numbers too. I'm going to redraw this so we can do the actual math. And just remember that string was 3/4 of the way up. The center is always the center. I'm going to take some measurements with my happy protractor here, and we will see what those angles are, and I'll write them down, and we'll get to do some math with those to calculate torques for that example. And I am standing next to the fire. I did that on purpose because what I'm going to have us start doing are some physics fireside chats. All right, I know a lot of your teachers are having virtual class meetings. I haven't done that yet. I've been posting videos and creating a lot of those because sometimes the fireside or the group meetings done like that are harder to control. But we're going to keep making torque videos. We're almost done with that. Then we'll get into moment of inertia, and then we'll just keep going. And remember, we're going to stand next to our fire. We had a few more seconds left.